Welcome to your fourth lab for Physics 187. Today we're going to take the first step in measuring the distances to the stars. And this lab will consist of 4 parts. The first part will just be a series of exercises to refamiliarize you with the idea of trigonometric functions and how different sides of triangles are related to each other. The second part of the lab will take those ideas and actually apply them to stars to show how we would calculate the distances to those stars. The third part of the lab helps you calibrate a telescope so you can actually make the measurements that you see for those stars. And the fourth part of the lab actually helps you measure the distance to those stars. If you remember what parallax involves, is that for nearby stars we can actually see an apparent shift in the position of these close stars with respect to the background stars as the Earth moves around the Sun. That shift is very, very small because those stars are very far away from us. And it took astronomers quite a long time to be able to come up with measuring systems that were accurate and precise enough to be able to allow us to measure those very small shifts in angle. Astronomers also came up with a very convenient way of determining that distance, having very simple calculations. That is, if you can measure that parallax angle in units of arc seconds, then to determine the distance to the star in a new unit of measurement called a parsec, you just take that parallax angle and divide it into 1. And that's very easy math and allows astronomers to find the distances to objects in this unit of parsecs with very simple mathematics. We can also convert the parsec to a light year with a very simple conversion factor. 1 parsec is equal to 3.26 light years. Let's remind ourselves a little bit of the math that we're going to be doing for this particular lab. You may remember having a right triangle with 2 sides and a hypotenuse and some angle. We'll label the 2 sides, the longer of these 2 sides A, the shorter of these 2 sides B, and the angle that we're going to measure we'll use as capital A. And then astronomers realize, well, geometers realize that triangles that have a right angle and these same set of angles always have the same ratios for the different values of the sides. And so they define the ratio of the side opposite to the side adjacent for this particular angle as a function called the tangent. And they just then define the tangent of this angle A as the ratio of these 2 sides, which we're representing as B over A. Now we said that for parallax, the angles are going to be really quite small. And astronomers then realized that if these angles are very small, you can actually simplify this equation even more. If you measure the angle in radians, then if you take the tangent of that angle in radians, the value of that is actually equal to the value that you put in there. And so the tangent of A, we would just simply say, is equal to A. And that we can represent in this equation right here, where the angle A is equal to the ratio of B over A. Now this extra factor here of 180 over pi is, remember I said if we measure the angle in radians, then the tangent of A is equal to A. If we measure the angle in degrees, it doesn't quite work that way. And so what this just simply does is the conversion factor that takes that and converts it from degrees to radians. So, if we have an angle, we can then find the value of the sides of the triangle. So if I know the side B and I know the angle, I can find the value of this long side A, or if I know the value of the long side A and the angle, I can find the value of the short side B. The first part of virtual astronomy will just be some practice for you to help find the unknown sides of the angles. So, they give you the short side of the triangle and they give you the angle in arc seconds. The first thing you need to do is convert the angle in arc seconds to the angle in degrees. And that conversion factor is available for you in your lab manual. Once you have the angle in degrees, you can then use that angle in the equation that I just showed you before to find the value for this side A. You're given the value of the short side B, you're given the value of the angle, which you have to convert to degrees, and then you can use that to find the value for A. When you perform this lab, I would suggest that you use a table as shown in the lab manual to help you keep track of things. So for example, problem 1, the angle, the arc seconds, the value for A and the value for B, and then just simply circle the answers that you had to calculate, right? So for this first one, you would circle the angle A here because that was the value you calculated, and you would circle this value for the side because that was the value for you calculated. You don't need to do screen captures for this particular lab. If you just put your answers in this table, I'll be able to verify on my own if you did the calculations correctly. You're asked to do 5 different questions, ideally 5 different ones so that you're not calculating the same values each time. If you've generated a new question and you're asked to do the same thing 3 times, the next 4th one is the same calculation again. Skip a couple until you have had to calculate, for example, the angle in degrees, the side B. You've had to calculate at least one of these values in each of these columns. So this first part then just gives you a little practice with the math. How do I use the various sides and angles of a triangle to get the unknown values? The second part of the lab then has you apply those ideas to actually calculating the distances to objects. So this, for example, is showing you how the parallax is calculated, right? We're looking at how the star shifts with respect to the background stars as the Earth moves in its orbit. And then you're told the parallax angle in arc seconds. If you're given the parallax angle in arc seconds, the calculation that we showed you before is just you take 1 over that value, and that will give you the distance in parsecs, and then you need to multiply that distance in parsecs by 3.26 to get the distance in light years. Check your answer, move on to a new question. The next question now gives you the distance in parsecs and asks you to find the parallax angle in arc seconds. Again, it's the same idea. If the distance is 1 over the parallax angle, then the parallax angle in arc seconds is just going to be 1 over the distance. And once you have the angle in arc seconds, you would use the same conversion factor to convert from arc seconds to degrees. Remember, an arc second, there are 60 seconds of arc in a minute and 60 minutes in a degree. So 1 arc second is equal to 1/3600th of a degree. Continue on with new questions. And just like you did for the previous exercise, for this one, you will also have a table that you should fill out for this. Again, where you circle the answer that you were asked to calculate for that particular problem. After you've had some practice with using angles to determine distances, we'll then go on to measuring the actual values for some stars. The first thing you need to do is you need to calibrate your telescope. So let me just jump ahead and show you what your field of view will look like. You will have a grid, you will turn on the animation, and this will move the Earth. And notice that these stars, as the Earth is moving, are moving back and forth in the sky. They're showing a parallax shift. In order for you to be able to measure the value of that parallax shift, you need to figure out how many arc seconds each one of these squares is worth. So to do that, we go to exercise number 3, which has you calibrate the telescope. Right now, my telescope is tracking these stars across the sky, and so the stars don't appear to be moving. When I turn off my tracking on the telescope, notice what happens is these stars begin to move across the sky. And while you can't quite see it on this screen, on the very top of this menu bar, let's see if I can adjust the monitor. Notice on the very top there's a T equals with the clock running. So you have a clock on the top of that menu bar to help you keep track of time. To figure out your field of view, what you need to do is determine how long it's taking these stars to move across the sky. Let me stop the telescope or track with the stars. And here's what you want to do. You want to stop this so that you have a star as close to this edge as possible. Stop the telescope so that you have a star as close to this edge as possible. I haven't done a very good job of that yet. Let me try one more time. I'm going to do this very slow. Still not quite very good. So you may need to do the same thing I'm doing here. There. Now I have a star that's very close to the edge. What I want to do is I want to take time, the amount of time it takes the star to move across my field of view. So I would write down the starting time, and then when the star gets to the other side of the screen and just begins to move off my screen, I would stop this and write down the stop time. I want to do this for 5 stars as they move across the field of view. Don't try to do this for 5 stars all at the same time. Repeat what I just did, which is wait till you have a star that's just barely visible here, and then track it and move it across the field of view. Measure the time for those 5 stars and record those in the table for that particular field of view. What this gives us is it gives us the transit time for this star to move across the field of view for this particular telescope. To figure out what the field of view for your telescope is, we're going to use this simple idea. Going to move over to this place right here. To find the field of view of your telescope, you're going to take the transit time in seconds. Be careful because the transit time on your lab report is in milliseconds, so make sure you divide that time by 1,000 to get your transit time in seconds. So I'll take the transit time in seconds and I will divide by 86,400. 86,400 is the number of seconds in a day. So what this transit time is doing is it's telling me what fraction of a day have I covered as these stars move through this particular part of the sky. The ratio of transit time to the length of the day is going to be the same as the ratio of the angle I've measured to the 360 degrees it takes me to go once around the circle. So I can multiply both sides of the equation by 360 to tell me what my field of view is in an angle. And I don't want an angle measured in degrees. I want an angle measured in arc seconds. So I multiply by 3,600 to convert from degrees to arc seconds. This gives me the value for that field of view. And if you look at this field of view, you will notice that there are 10 squares. So you take the value of your field of view and divide by 10, and that will tell you what each one of these squares is worth in arc seconds. It sets the scale for your telescope. Once you have the field of view for your telescope and how many arc seconds each of those squares is equivalent to, now you're ready to measure the parallax angle for these stars. I'll go ahead and start the animation. And what you need to do for each of these stars is measure. Let me just focus on this bottom star. Right, you'll need to measure the angular width from here to here. And that will give you twice the parallax angle. Remember, the parallax angle is determined by this to this corresponds to the Earth moving all the way around its orbit and the parallax angle is defined as half of that angle. So make sure once you measure that distance, to give you that width of that shift, make sure to divide it in two before you use that value for the parallax angle to measure the distance to the star. This lab requires very, 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 very careful attention to detail. You can get all of the answers to check if you are very meticulous with your measurements. But remember, especially if you have small parallax, a very, very small error in measuring the parallax can result in a very large error in the distance. And so you may get a parallax angle to check, but when you take the inverse of that, the difference in that will be very big. I remind my students that we can measure parallax angle down to about 1/100th of an arc second. So if we're measuring a parallax angle of 0.202, it could be maybe 0.015 or 0.025, all of which seem pretty close. But if the parallax angle is actually 0.2, that corresponds to a distance of 50 parsecs. If the parallax angle we measure is 0.25, that only corresponds, or 0.025, that corresponds to a distance of 40 parsecs. And if it's 0.015, that corresponds to a distance of almost 65 parsecs. So a very small error in that angular measurement can result in a very large error in distance. Good luck with the lab. My advice is to pay very, very careful attention to measuring those angles when you're measuring this parallax shift. If you have any questions, please email me.